Hi everyone. For this video, I'm using this wonderful little computer program that I also gave you guys the link to. You can see it up here on the computer screen for coloring in the multiples. When you do this in your class though, I think it's probably better for the kids to do this on a piece of paper and a crayon or some colored pencils or whatever, so that they can more slowly explore how the multiples work. So here goes. I'm going to choose multiples and I'm going to click on the 2 and it's going to show me all the multiples of 2. So you see how it's highlighting one at a time. This is a lot of fun. It's also like when you do skip counting in your classes. So in your classes you're going to have the kids recite the even numbers or multiples of 2. 2, 4, 6, 8, 10, 12, 14, 16, so that they get good at skip counting, skipping those numbers. Now, what I want you to look at is the pattern, and this is what you're looking at with your students when you teach. What's the pattern of all of the multiples of 2? You probably know this one already. If you look at all of the multiples of 2, what do they always end in? And you can work on this with your students much more gradually. But for us, it's a little quick. We know the multiples of 2 always end in 2, 4, 6, 8, or 0. And you'll know a number is a multiple of 2 if it ends in one of those. Now, what if we decide we want to look at multiples of 3? So I used the little eraser to clear out my multiples of 2. Now I'm going to click on the multiples of 3 and make them be yellow. So I chose the yellow color here. Now let's look at the multiples of 3 and see if we see a pattern for the multiples of 3. What do they end in? I kind of see this cool diagonal pattern here. So that's something neat to look at. And let's look at the endings. Well, some of them end in 2, but they don't all end in 2. Some of them end in 1, but they don't all end in 1. It doesn't look like there's a pattern to the ending numbers for the multiples of 3. So let's take a look at the multiples of 3 on a piece of paper. So I've written down the multiples of 3 on this piece of paper here. 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9. If we were skip counting, we would just say the answers: 3, 6, 9, 12, 15, 18, 21. Let's fill in the last one here. 8 times 3 is 24. Can fill in the next one. 9 times 3 is 27. 3 more. 24 plus 3. Now let's see if we can see anything about the multiples of 3. I don't see any pattern in the ending digits again. But what if you took the digits here and added them up? So I know the answer is 12. Suppose we take 1 plus 2 and add it up. And here the answer is 15. So what do we get when we add 1 plus 5? And then 1 plus 8. Take a minute to add the next couple and see what you see when you add them up. This one's 3. This one's 6. This one's 9. Do you see a pattern now? Add the next couple, and I'll just wait a sec and see if you see that pattern continue. So the pattern of the 3s is not a pattern of the ending digits. The pattern of the 3s is a pattern of what they add up to. So 2 plus 1 is 3, and we not put an equal sign there, just adding the digits. And you can see a 369, 369 pattern emerge. This one adds up to 6. This one adds up to 9. You can tell if a number is a multiple of 3 because the digits add up to a multiple of 3. For example, the number 1, 1, 1, I know that's divisible by 3 because 1 plus 1 plus 1 is 3. Try it on your calculator. Try dividing 1, 1, 1 divided by 3. Let's see what I get when I try that. 1, 1, 1 divided by 3. And look, you can see it goes in evenly. And so that's the pattern for the multiples of 3. It's very different. Now let's go back to our times table again. How about the multiples of 5? What's the pattern there? And again, your kids should be able to skip count by 5s. 5, 10, 15, 20, 25, 30. That's skip counting by 5s. Do you see a pattern? Is it that I had add up the digits? 1 plus 5? 2 plus 5? No. It's that they always end, multiples of 5 always end in 5 or 0. What about how can I tell if something's divisible by 6? So for 6, actually, there isn't a special rule all on its own. For the multiples of 6, what I do is I look for the multiples of 2, and then I can pick a different color if I want, and I'm going to look for the multiples of 3. They're catching up to each other. Now, the ones that are divisible by 6, if you look, 6, 12 is divisible by 6, 18 is divisible by 6, 24 is divisible by 6. They're the ones that I colored twice. So the rule for divisibility by 6 is it has to be divisible by 2 and by 3. And that's true of a lot of the slightly larger numbers, right? You know if it's divisible by both numbers that go into it, that's how you can tell if it's divisible by that number. For instance, a number is divisible by 15 if it's divisible by 3 and by 5. Now, the rules that I've given you so far, I want you to memorize, and they are summarized at the end of this first section. So please take a look at the summary as you do your homework and refer to the rules as you do your homework. But I just want to warn you, with kids, you don't make them memorize this. You let them figure it out. That's the whole idea, is exploring. So right now I want to explore just a really cool pattern with you, which is the pattern of 9s. First of all, the multiple of 9s make this really super cool diagonal. That's one cool thing. The second cool thing about the multiples of 9 is look at what happens when you add the digits up. So 1 plus 8, 2 plus 7, 3 plus 6, it adds up to 9. Or if you go higher, like 99, it adds up to 18, which is a multiple of 9. So the rule for 9s is just like the rule for 3s. That's pretty awesome. But it gets even more awesome, and it's a really fun pattern to explore with kids. So, whoops. So if you look at this chart, you can see some of the more interesting stuff that happens. So I put a 0 in here so you could see the pattern. Look at this: 0, 1, 2, 3, 4, 5. Those are my answers, right, to the multiples of 9. See if you can think, okay, what's going to go right there, just based on what's pattern is happening as we go down. And now look on this side and look at what's happening here. 9, 8, 7, 6, 5, 4. What do you think is going to go in the ones place here, just based on the pattern? So based on the pattern going down the table, you know 7 times 9 is going to go up 1, right? It's going to go 4, 2, 3, 4, 5 is going to be 6. And then it's going to go down 1 here. 8, 7, 6, 5, 4, 3. But it gets even better than that. Look at this 7 right here, and then the 6 right here. What do you notice about this number that's in the tens place? Look up here. Look at the 3. And what number is in the tens place? A 2. Look at the 5. What number is in the tens place? A 4. Plus, they both have to add up to 9, right? So how could we do 8 times 9? We can just go, okay, if it's an 8, it's going to be 1 less here in the tens place. So it's going to be a 7. And then it has to be a 2 because they have to add up to 9. Wow. You could do that here with 9 times 9, sorry. 9 times 9, it has to be 1 less than 9, which is 8. And there has to be a 1 because 8 plus 1 adds up to 9. So that's how I got through my nines times tables. I did not memorize them. I just knew the pattern was always one less in the tens place, and then the ones place had to add up to 9, the 2 digits. I would not have survived the times tables if I didn't have this. Now, some of my students showed me this really cool thing that comes out of this, which is this finger trick. So can you see me in the corner there? Oh, I think I'll switch to the big screen. Hang on. All right, so here's the finger trick. If we want to do 3 times 9, bend down your third finger. 3 times 9 is, you have 2 fingers here. Face the right way for you guys. Uh-oh, this is kind of backwards for you. You're going to have to try this yourself. Right now, trust me, this is backwards. So 3 times 9 is 20, 27, because you have 2 fingers left over here and 7 fingers left here. And let's try 4 times 9. So 4 times 9, bend down the 4th finger, is 36. But when you try it yourself, it'll be the right way around for 36, right? For you guys, it looks kind of like 63. Sorry about that. So the thing about the finger trick, it's super cool, is that I wouldn't teach it without teaching why it works. If you are doing 3 times 9, you're bending down the 3rd finger, right? So that leaves 9 fingers left. And you have 2 fingers on one side and 7 fingers on the other side, so they have to add up to 9. And it's 1 less than 3 because you bent down the 3rd finger. It works because of the pattern. I don't like it math being just magic. I like there to be a good reason, because if math is just magic, then ordinary people can't do it. Only magic people can do it. And I think everybody can do math. So with that, let's end this with my other favorite thing to do with this table, which is we're going to switch from multiples to automatic. And we're going to just have it start coloring in the multiples. So it's going to color in the multiples of 2 first and make them go away. This is called the sieve of Eratosthenes. We're taking all the multiples of a certain number, let's speed this up, and we're making them go away. No, that slowed it down. Whoops. There we go. And now we're taking the multiples of 3 and making them go away. Now the multiples of 5. Now the multiples of 7 are gone. I can't keep up with this. We're taking the multiples of... I lost track of what we're taking the multiples of, but basically, when you do this at home or with your students, you're circling a number and then removing all its multiples. Circling the number 3, removing all its multiples. Circling, we already had crossed out 4, so we circle 5 and remove multiples of 5. We had already crossed out 6. We go to 7, cross out all the multiples of 7, and keep going. Now look at the numbers that are left, that are in the white boxes. What kinds of numbers are those? Look carefully. The numbers that are left are 2, 5, 7, 11, 13, 17. Those are all numbers that where we crossed out their multiples, and they were the first one, right? They are not divisible by anything except themselves and 1. Those are the prime numbers. So you've just been introduced to this very ancient sieve of Eratosthenes from ancient Greece on a brand new computer program that gives you prime numbers.